Empirical versus theoretical probability. Welcome, everyone. Today, we are going to explore a fundamental concept in probability. As we begin our study, it is important to recognize that when we want to determine the likelihood of an event occurring, we generally encounter two primary methods, the empirical approach and the theoretical approach. Now, while both of these methods share the same ultimate goal, which is to quantify uncertainty and give us a numerical value for how likely something is to happen, they differ fundamentally in their starting points. One relies on what we observe in the real world, while the other relies on mathematical logic. Over the next few slides, we will break these two approaches down individually, look at some practical examples, and ultimately see how they compare to one another. 1. Empirical probability. Now that we've introduced the two main approaches to probability, let's dive deeper into our first method, empirical probability. You might also hear this referred to as experimental probability. The key thing to remember here is that this method is rooted in reality. It is based on actual observations or data that we collect from performing a series of trials. Unlike the theoretical approach we will discuss later, which deals with ideals, empirical probability describes what actually happened during a specific experiment. To put this into a formal definition, the empirical probability of an event, which we will call E, is simply the ratio of the number of times that specific event occurred to the total number of trials we conducted. If you are looking at the mathematical formula, it is written as P of E equals the number of trials in which the event happened, divided by the total number of trials. So, as we move into our next slide, keep in mind that we are essentially just counting successes and dividing them by our total attempts. We'll use a coin-tossing example in a moment to show you exactly how this calculation works in practice. Real-world example, tossing a coin. Now that we understand the definition of empirical probability from the previous slide, let's look at a concrete, real-world example to see how we actually calculate it. Imagine you decide to perform an experiment where you toss a coin 50 times, specifically to track how many times it lands on heads. To find our answer, we'll follow a simple step-by-step calculation. First, you conduct the experiment by physically tossing the coin 50 times. Second, you must record the outcome. For this example, let's assume that after all 50 tosses, you counted that heads appeared exactly 28 times. Third, we need to identify our variables for the formula. Our number of favorable outcomes, which in this case is heads, equals 28. Our total number of trials is 50. Fourth, we apply the empirical probability formula we just learned. We take the number of successes and divide it by the total number of trials, so the probability of heads equals 28 over 50. Finally, we simplify the result to make it easier to interpret. 28 over 50 simplifies to 14 over 25, which, when converted to a decimal, gives us 0.56. So, in this specific experiment, the empirical probability of getting heads is 0.56. Notice how this value is slightly different from the theoretical value we will explore in the next slide. 2. Theoretical probability. You will often hear this referred to as classical probability. Unlike the empirical approach we just discussed, theoretical probability isn't about what did happen in a trial. Instead, it is based on mathematical reasoning and the fundamental assumption that every possible outcome is equally likely to occur. Think of it as describing what should happen in a perfect, ideal scenario. If you look at the definition here, you'll notice a key distinction. We calculate theoretical probability without performing any actual trials or experiments at all. We don't need to flip a coin 50 times like we did in our previous example. Instead, we rely entirely on the known properties and the inherent structure of the experiment itself to determine the likelihood of an event. So you might be wondering, when is this actually useful? Well, theoretical probability is absolutely essential in situations where conducting physical trials is unfeasible, far too expensive, or even dangerous. For instance, consider the launch of a satellite. It would be incredibly impractical, and certainly too costly, to launch 100 satellites just to observe how many of them fail so that we can calculate a failure rate. In a case like that, we cannot rely on empirical data from repeated trials. Instead, we use theoretical models built upon established engineering data to predict the probability of a successful launch. This allows us to prepare for risks without having to undergo the actual physical experiment. Now that we have explored empirical probability, which, as we just saw in the previous slide, relies on recording actual data from experiments, let's shift our focus to the second primary method, theoretical probability. Real-world example, tossing a coin. Now, let's move from the experimental side of things to the mathematical side. On the previous slide, we looked at an empirical example where we actually tossed a coin 50 times and got a result of 0.56. But now, on slide 5, we are going to look at theoretical probability. To do this, let's consider a fair, unbiased coin, meaning a coin that isn't weighted to land on one side more than the other. Unlike our previous experiment, we aren't going to actually flip anything. Instead, we are going to use pure logic. Let's walk through the step-by-step calculation together. First, we need to identify all possible outcomes. If you look at a standard coin, it has only two sides: heads, which we can denote as H, and tails, which we can denote as T. Second, we determine the total number of outcomes. Since we have heads and tails, the total number of possible outcomes is 2. Third, we identify our favorable outcome. In this specific problem, we are looking for the event of landing on heads. Looking at our list, there is only one such outcome. Fourth, we apply the logic of the theoretical formula. We take the number of favorable outcomes and divide it by the total number of possible outcomes. Finally, we calculate the result. 1 divided by 2 equals 0.5. So, in this case, the theoretical probability of getting heads is exactly 0.5. Notice how this differs from our empirical result of 0.56 from the last slide? As we will see in our summary later, these two numbers don't have to match perfectly in a small experiment, but they are closely related. Now, let's look at how these two different approaches compare side by side. Comparison summary. Now that we have looked at the individual definitions and worked through our coin-tossing examples, let's bring everything together. This summary table is a great tool to help you distinguish between these two approaches at a glance. First, let's look at the basis of each. Empirical probability is grounded in reality. It is based on actual trials or data that you have collected. On the other hand, theoretical probability is grounded in mathematics. It is based purely on logic and reasoning. Next, consider the requirement. For empirical probability, you have a practical requirement. You must actually perform the experiment and record the results. However, for theoretical probability, no experiment is required at all. You can determine the probability just by analyzing the possible outcomes. This leads us to their nature. If you are looking at empirical probability, you are describing observed results. Essentially, you are reporting what did happen. But with theoretical probability, you are describing expected results. You are predicting what should happen in an ideal world. Finally, let's look at the formulas to ensure you don't mix them up. For the empirical approach, the formula is the number of successful trials divided by the total number of trials. For the theoretical approach, the formula is the number of favorable outcomes divided by the total number of possible outcomes. As we move to the next slide, I want you to pay close attention to a few common mistakes students make when trying to apply these two different formulas. Common mistakes. First, let's talk about the misconception of expecting exact matches. Many students believe that because we have a theoretical value, our experimental results should match it perfectly every single time. But that is rarely the case. For instance, as we saw in our previous examples, the theoretical probability of a coin flip is 0.5. However, if you were to actually perform an experiment and get heads 6 times out of 10, your empirical probability would be 0.6. You might feel like you've done something wrong, but you haven't. It is vital to understand that empirical results fluctuate due to random chance. However, here is a key concept to remember. As you increase the number of trials, meaning as you toss that coin hundreds or even thousands of times, those experimental results will tend to drift closer and closer to that theoretical value of 0.5. Second, a very common mistake is using the wrong formula. It is easy to mix up the denominator in your fractions. When you are working with empirical probability, you are looking for the total number of trials, the actual number of times you performed the experiment. But when you are working with theoretical probability, you are looking for the total number of possible outcomes, the total number of things that could happen in a perfect scenario. To avoid this error, I want you to always ask yourself this one guiding question. Am I looking at data collected from an experiment that has already happened, or am I looking at the mathematical possibilities within the system itself? Keeping this distinction clear will ensure you apply the correct logic every time. Now, before we wrap up, I want to pause and address some common pitfalls that students often encounter when working with these two types of probability. It is very easy to get tripped up if you aren't careful with your approach. Key takeaways. First, remember that empirical probability is retrospective. Think of the word retrospective as looking backward. This method is all about looking at the data and the results that have already occurred through actual experimentation or trials. On the other hand, theoretical probability is prospective. This means it is forward-looking. It uses logic and the structure of the event to predict what is likely to happen in the future, even before any experiment has even started. As we discussed earlier with the example of the satellite launch, remember that theoretical probability is our preferred method whenever conducting physical trials is simply impractical, too expensive, or even impossible. Finally, regardless of which method you are using, whether you are analyzing experimental data or using mathematical reasoning, the probability of any event, let's call it event E, will always be expressed as a value between 0 and 1. All right, we have reached the end of our lesson, so let's wrap everything up with these key takeaways to ensure you have a solid grasp of the topic. I hope this distinction between what actually happened and what should happen is clear now. Great job today.